Thank you very much for taking the time today to view our video. Before we begin, we'd like to take a moment to introduce ourselves. There are many aspects to 9.Connects, but it boils down to the fact that we're a PCB-centric organization. We believe and focus on the PCB due to the fact that it is truly the center point of all electronic design. That's where our expertise lies. We provide services not only in the PCB layout, but in design consulting as well. And during the technical portion of this webinar, you will see this expertise in motion. We are now the exclusive North American instructors for Altium Designer. We host 100 trainings throughout the year across North America, and we are excited to bring these trainings closer to you. In addition to our services, we are also a value-added reseller for a number of PCB-related software companies. And just to note, each company has been presented in past webinars. So if you're interested in them, please contact us or check out our website. And by the way, we provide one-on-one coaching for these tools as well. For more information on our services and past webinars, please contact us. Our information is listed in the description below. Thank you for giving us a moment of your time, and please enjoy the presentation.
We're going to start part 2 of our 3-part series of the Engineer's Engineer. We're going to be talking about electromagnetics and signal integrity, and in particularly we're going to focus on intuitive fundamentals. And there's a reason for intuitive, and we'll get to that in a moment. In terms of topics, we're going to be focusing primarily in this one on fields and resonators. Later on, we'll deal with other traces in section 3. The purpose of this is to provoke consciousness and thinking about electromagnetics and signal integrity. People tend not to think about it until the very end and then try to throw it in, and it generally doesn't work. We need to have a framework upon trying to deal with it in an intuitive way only. Trying to open a box of new vantage points by which you can see things from a different light and feel them in a more intuitive and hence welcome way. So why is intuitive important? Well, first, let me start, first and foremost, detailed materials abound. Lee Ritchie, Howard Johnson, Bob Pease, and lots of app notes, calculators. You need to know them. You need to understand them. What I'm going to tell you today is not a substitute for that. However, oftentimes these things are very complex and you take weeks going through them, or you spend several weeks in a course, and you oftentimes can't see the forest for the trees. So what is necessary in a real design is to scan for potential problems fast before calculating the solutions to fix particular instances in there. Much of the thinking that we do is a set of vantage points. And so if we can give you a new set of vantage points, it will enable you to think outside the old box to see things clearly. 9.Connects experts are here to help you see things in different ways. In terms of the topics that we're going through today, we'll start with electric fields, voltages, and capacitance. We will touch on magnetic fields, currents, and inductance, but that's really going to be more applicable to section number 3. And we're going to focus primarily on resonances and antennas. In the next section, we'll be looking at propagation, termination, impedances, matching and splitting, those kinds of things. But we're not going to look at those today because there's just too much material to cover. We're going to start with point charges. A charge that is at a point has at one point, i.e. it's absolutely zero, approximately. However, point charges of zero size don't really exist. Things like protons and electrons have sizes in the order of femtometers. However, when we are far from a cluster of charges compared to the size of the cluster, the effective field approaches that of a single point. For example, we can talk about ionized particles like dust. They're very small, so when we're more than about 10 times the diameter of that particle away, any charge that's on it will look very much like a point charge. Another thing might be a tiny metal bar, say a millimeter cube. Well, that's missing a few electrons to have a charge. Well, when you're a centimeter or more away from it, that will look pretty much like a point charge in terms of the electric field that is coming up. So, in talking about point charges, they have electric fields. The charge at a point is called a point charge. We just call it that by definition. And in the image at the right, you'll see the lines radiating out in a thread bath in oil that show the electric field lines, the actual field lines from a point charge. Of course, the dot in the center is not an exact point, but it begs the point that it still looks the same if that were a point charge. A charge can be either positive or negative. By convention, we say that if the field lines are going outward, that's called a positive charge. If the field lines are going inward, radially, we call that a negative charge. So let's assume that we have a point and we have a field from it. And let's say that we position a sphere at the center of that point. All of the field lines that pass out from that point charge will pass through any hypothetical sphere centered at that point. Because the surface area of the sphere increases like the square of its radius, then at any distance the field intensity per unit area drops off like the square of the radius. This is important. In talking about what the effects from multiple charges are, we have to add them together. For linear fields, of which electric and magnetic fields are linear, the field resulting from multiple sources is merely the sum of the fields resulting from each individual source. However, electromagnetic fields have both direction and magnitude, hence they are called vector fields. And the vector sum is what we need at each point, which means we're actually doing an addition of the arrows. Superposition of two static fields is added by summing the arrows in three-dimensional space. Note that this gives rise to the classic curved field shapes that we see for the sum. If you have two different charges, field lines will be going out from one charge and coming into the other. Those field lines that emanate from the positive charge will land on the negative charge. If the field is equal and opposite, they will all land there. The dashed line in the middle is the point that's is a plane that is equidistant between those charges, and you'll see that all the field lines cross at right angles at that point. If we happen to have the same charge, it's different. The two plus charges push the field lines away, and they all radiate out. None cross the dashed red line in the center. Remember, we're talking about 3D around points, and the above is merely a 2D representation. It's only a slice through 3D. So when we have the same polarity electric fields, that the resulting superimposed field lines push apart in the vicinity of the sources, and all field lines extend to infinity. That's a very important thing to remember. Very far away, compared to the distance between the points, the resulting field pattern approaches that of a single point with twice the charge. If you have opposite polarity electric fields, the majority of the superimposed field lines terminate on each other in the vicinity of the sources, and few extend to infinity. You can see the shape by the image in the middle between two oppositely charged points. That's very similar to the drawing that you see in the left, where you see field lines emanating out of the plus charge and going into the minus charge. On the right, you'll see a field between 2 points that's done in a vector form. The little arrows show the direction and magnitude of the field. Close in between the points, you'll see very, very high gradients and very, very high fields. But as you go away, you'll notice that it turns dark blue. That means the field is rapidly dropping off in intensity. And by the time you get to be 10 times as far away from those pair of points as their distance apart, you'd see it being very blue, and very, very little electric field would be there. So very far away compared to the distance between the points, the resulting field pattern approaches that of a single point having the charge difference. However, if the charges are equal and opposite, they will vanish, and no lines will go to infinity. That's the reason for pairing opposites. The cancellation of fields at a relatively far distance is very much enhanced if they are equal, opposite, and close together. That's the basis of differential pairs. So let's reiterate. Keys to electric field coupling reduction. First, assume you have two sources, A and B. Keep the source voltage differences equal and opposite, i.e. differential. That helps them to cancel. Keep the spacing between them much closer than quarter wavelength at the highest harmonic of interest. That's not so easy to do. But understand that if you're talking about in the AB direction or the BA direction, that if the wavelength if that's equal to a half wavelength, then you will have completely inverted the charge of an AC signal. So it's important to understand the wavelengths. Keep everything else very, very far away in comparison to their spacing, and it will cancel. If you can't keep them equidistant, then you also have the fallback position of keeping them equidistant from each source. In other words, A to C is the same as B to C, and in that way they will cancel by being equal with the distance. So let's talk about near versus far fields. And again, this is an approximation. An antenna person would probably take exception to the words that I'm saying because I'm abbreviating them very much. But objects collectively creating fields have sizes and distances with respect to each other. And they create fields that are fairly close. So when you are close to these objects, the fields can be quite complex. These are called near fields. And they are, in effect, when you are close to them compared to the distances of their sizes with respect to each other. When you are much, much further away from these objects than their largest sizes and distances, then the fields simplify. And these are called far field effects. They are quite different. So we need to point them out separately. Let's take a look at a little bit of this. Static electric field around a line is different than it is from a point charge. It, however, happens to fall off like 1 over the radius instead of 1 over the radius squared as a point would. Well, why is that? Well, in the vicinity of the electric field, it is radially outward from the line, but it is not radially outward in the direction of the line. If you look down at the bottom, you'll see a line segment, and you'll notice that in the center, the green arrows are pretty much directly out from the line. But if you look at the end of the lines, you'll see the arrows are starting to bend off. When you are very, very far from the line segment, then it will start to appear as a point, and you will have a 1 over r roll-off. However, when you're close to the line with respect to its length, it will exhibit a 1 over r roll-off. So that's an important thing to think about. How far away does a linear segment have an effect that rolls off like 1 over r? Science repeats itself, be it wires, speakers, or PCB traces. Bose came out with a set of speakers called cylindrical resonators. Actually, they were invented back in the 20s because I read about them in a book from the 30s. But it's a fairly tall antenna that radiates at all levels directly outward. Because it is a linear radiator, the roll-off in the close field, the near field, is like 1 over r instead of like r squared. This near field distance is roughly equal to its height, i.e. the length of a line segment. It's great for musicians because they can wander around further without the sound of their monitor falling off, or in crowded lobbies where you don't want it to be too loud in one place and not able to be heard in another. If you've ever been to a bar that boasts of being a mile-long bar, they'll have mirrors on one end and on the other end, and if you look down there, the reflection between the mirrors makes it look like it's very, very long. The same is true with a cylindrical radiator like this. If it's on a reflective floor and there's a reflective ceiling nearby, it will make it effectively look like it has a much longer length due to the reflections, and hence the 1 over r field distance will be much, much further. So there are several different manufacturers that make these, and they are very useful. So what is this? Could that be a cylindrical radiator? Food for thought. Static electricity around a plate is a little bit different. The static field near the face of a plate doesn't fall off like 1 over r squared for a point or even 1 over r for a line. In the close vicinity, the electric field is collinearly outward from the plate. All the lines are equal. You can see that in the capacitor down at the bottom. It goes equally between plates. The same is true if you have a single plate. However, it doesn't fall off at all if they are collinear. However, once you get far from the plate in comparison to its dimensions, it starts to act like a point source. So many people are only familiar with a capacitor, and so the concept of having a single plate and charge from it is new to them. But it is quite valid to say that. You'll notice in the image at the right that the reddest intensity is right around the corners of the plate, and that's where you have the highest curl and the highest divergence. In the middle of the plates, it's very even up and down field, and when you get far away from the capacitor plates, you'll notice the field drops off rapidly. You'll also note that it's almost nothing in the middle on the sides outside the plates. Again, this all has to do with the electric field, near field, and far field around a plate. So what is this? Many of you, I'm sure, know what it is. Well, let's talk about it. Let's start off with a ground, which we have defined as 0 volts. Okay? Then to that, let's add a conductor, a vertical one in this case, and tie one end of it to the ground. What we end up with is a vertical end reference, a vertical conductor end reference to ground. there is a node there, and any place where the node's short to ground, the voltage has to be 0 because it's shorter to ground. However, that doesn't mean the current needs to be 0. It can certainly not be 0. On the other end, you have an open, and any place that a conductor ends with an open, the current must be 0. But that does not mean the voltage of that place needs to be 0. So, what is this? Well, of course, many of you recognized it as the Eiffel Tower. It was built over a century ago and has a height of almost 1,000 feet. However, with its height of a little over 1,000 feet, it has been used for over a century as an antenna. Thus, it might be more aptly called the Eiffel antenna. It was used in 1898 to translate broadcasts to the Pantheon. Again, this was done with long wave because it's a very tall structure, and so it fit very well with the low frequencies of the day. It was used in 1913 to broadcast all the way to Arlington, Virginia, and it continues broadcasting to this day. However, in current days, they don't use long wave very much, so antennas have become smaller and been mounted up on the top. Quarter wave antennas, that's what we're looking at. One end is a low impedance, which corresponds with high current but low voltage. The other end is a high impedance, which corresponds with low current but a high voltage. The fundamental resonant frequency has to have a wavelength 4 times its length. That's why we call it a quarter wave antenna. Odd multiples of this fundamental will also resonate on it, i.e. n times a quarter wave. So what can we do with that? I don't know, let's take a look at a typical signal trace. Here we have a signal trace. It has a driver reference to low end so they can strongly drive the signal to make sure it gets to the end. The trace goes a particular length to a receiver, which is probably high impedance. Now we have a classic signal that's going down there. It has rising and falling edges and flats in between. Well, the flats in between, where it's low or high, typically don't have much energy. It's either high or low. But there's a high bunch of information, there's a high amount of energy that is required to make that transition in a very short period of time from low to high. That gives rise to edges that have a large number of some harmonic content. And so you get a spectrum that tapers off over a very large period of time. If it turns out that that length corresponds as an nth multiple of lambda over 4 to any one of those harmonics, you now have a quarter wave antenna that is being excited by that. And if you do that, then you're going to find out that it's going to radiate. And the other effect that it might have is it's going to distort the waveform by having resonances on particular harmonics and not others. So LC circuits also resonate. Are they equivalent? Let's look at it. Based on antennas are based on propagation speed and length, whereas LC resonators are based on lumped component values. Antennas are very large, about a quarter wavelength. Antennas are small, much less than a quarter wavelength in size. Antennas radiate well because their size is so close to that of a quarter wavelength in the propagation media that their radiation resistance is fairly low. Tank circuits resonate poorly because they are much smaller than the necessary quarter wavelength in the propagation medium, at least typically. As a result, antennas will radiate at all our odd harmonics, whereas tank circuits only resonate at the fundamental. So let's compare PCB traces. Are they similar to an antenna or different? Both are based on propagation speed and length, as opposed to simple lumped circuit elements. Both have significant effects when large in comparison to a quarter wavelength of the frequencies of interest. Both radiate well at resonance because resonance size is close to that of the wavelength in the propagation media, making the radiation resistance low. And both resonate at odd harmonics if not properly terminated. Assumptions and limitations apply. So let's talk about resonators. A resonator is anything which resonates at a particular frequency or set of frequencies. To do this, it has to have several things, 4 of them in particular. It has to have 2 or more energy modes, and there must be some mechanism by which that energy can slosh back and forth between the storage modes. It needs to have relatively low loss, so the sloshing doesn't damp out very quickly, and it needs to have some form of connection or radiation in and out of it by which it can interact with the outside world. So what about conductors? Can they be resonators? Well, they have 2 modes of energy. Because there are high impedance and low impedance points due to shorts and opens or low impedance drivers and high impedance receivers, they have at the high impedance ends, they have a significant voltage change, and they also have capacitance arising from that, so they can store a significant amount of 1/2 CV squared capacitive energy. Also, at the low impedance points, where a lot of current flows, they have an inductance arising from the magnetic field. Hence, they have a lot of 1/2 Li squared inductive energy in them. So yes, they have two forms of energy. Because of time and wavelength and separation, the current change associated by the current in the inductor over time will cause the capacitor to change voltage. And the voltage on the capacitor applied to the inductor over time will cause it to increase in current. So yes, we have a coupling mechanism between the two. We also have low loss typically because a wire dissipates energy fairly slowly. This means it will typically be undamped or relatively undamped. We also have radiation and connection between most of these circuits because they're typically driven at one end and received at the other, or something to that effect. Energy can get in and out. So let's talk about the frequencies. Any AC frequencies which meet all boundary condition constraints can energize and resonate such a conductor. If you have a resonator that is being impinged upon by any frequency components that meet that, then it will resonate. For this quarter wave antenna, the fundamental frequency has a wavelength 4 times the length of the antenna. That's obvious from us calling it a quarter wave antenna. Any odd multiple of this frequency also fits that constraint. So we have to be always looking at the harmonic content of the signal involved. Let's take a look at this. Let's take our antenna quarter waves that we talked about before. One of the constraints is that the voltage must be 0 at ground, but it can be very high at the top of the antenna. At the end of the antenna, where it's open, the current must be 0, but it can be very high where it's shorted to ground. We call this, because that's a quarter of a full wave, we call it a quarter wavelength antenna. Same thing is true for a third harmonic mode, which we call a 3/4 wavelength antenna. It is still meeting the same criteria. The current is 0 at the top and high at the bottom, and the voltage is high at the top and 0 at the bottom. But now it goes through more of a wavelength because the frequency is higher that is standing on it. We also can say something about the fifth harmonic mode, 5/4 wavelength long. It also meets all the boundary conditions, as does the seventh harmonic, which is 7/4 wavelength long, and all other odd harmonics fall in line. In general, if the top of an antenna, if a trace or a conductor has an open spot, it will be high impedance. Therefore, there will be little of any inductance current flowing. It will have high voltage. It can have high voltage. It will experience capacitance because the voltage can change, and therefore it will store energy like 1/2 CV squared. At the places where we have shorts, it will be a very low impedance, and hence it will have 0 or low voltage. It can have very high current, and because that current creates a magnetic field, there will be inductance, and they will have inductive energy stored as 1/2 Li squared. So we're not talking about antennas design here. We're talking about PCB design, but you have to understand that if your board is making antennas inadvertently, you're going to have resonances. You're going to have EMI propagating from it. You're probably not going to pass your radiated emissions, and you may not pass your susceptible emissions testing. So on the left, you see an image of a bunch of quarter wave whips. They have bases on them that typically mount to some large surface, like the top of an automobile. The automobile is large and conductive in comparison to the wavelengths involved, so it forms a pretty good ground. In the middle, you'll see an antenna that does not have a ground, so they've added radios onto it to make it have the equivalent of ground. In general, as shown on the right, if you have a poor ground, you can add radios to it to make it a better conductor so that current can flow in and out. They need to be at least a quarter wavelength long. At the very top, you can put a large piece of metal, like aluminum or something, and that's called a capacitive hat. It means that some of the current can flow in and out there and charge it up without the voltage going to extremely high levels. That's very important for making an antenna shorter and also preventing it from arcing over if you're trying to transmit with large amounts of energy. It reduces the voltage a lot. Any place in the middle of the line where currents are flowing, you can add an inductor to further shorten the antenna. But it's most common to put them near the ground plane where the currents are substantial. Here's an image of several capacitive hats, and We're not going to talk about them in detail, only wanted you to see them so that you can recognize that they do exist and understand why. So far we've talked primarily about quarter wave antennas, but there's also half-wave dipoles. Half-wave dipoles are essentially two quarter wave antennas stuck back to back. In the upper left you'll see a classic dipole which is open on the ends and in essence short in the middle. And because coax tends to be a very low impedance, like 50 or 75 ohms, they normally feed these things near the center. Down in the lower left, you have one that's a complete wavelength long, but that is just folded and flattened. That's called a folded dipole. You can see a tiny one in the fingers that's a half wavelength long. That only depends on the frequency of the fundamental as to what that size and length is. In the lower right, you'll see the most important characteristic. A half wavelength antenna is a half wavelength long. At the open ends, there is no current, but in the middle, there can be a lot of current. At the open ends, there can be a lot of voltage, but there is no voltage at the very center of it. These things can also be made in a short open short form instead of an open short open form by keeping the ends at low impedance and letting the center go to high voltage. That's shown in the two pictures above. One's an inverted V and the other is a rhombic. So let's talk about half-wave antennas. Either both ends are at a low impedance, which corresponds to high current at those ends, in which case the center will be at a high impedance, or both ends will be at a high impedance, which corresponds to low current, and the center will be a low impedance. The fundamental resonant frequency has a wavelength of twice its length for a half wavelength antenna. All integer multiples of this frequency will also resonate on it. So let's take a quick look at some resonant antennas. On the left, you'll see a representation of one which is grounded on the left and has a circuit feeding it partway up where the characteristic impedance of the antenna reaches that of the drive circuit for efficient energy transfer, and then it goes off to the end on the right where it is completely open and no current flows. That is the high impedance end. So that is in essence a quarter wave width. You can see that again in the piece of PC board that is soldered that has the penny in it. If you go over to the right, you'll see a component that has a little bit of a spiral that's open on the end. This is an antenna that can be purchased. If you look down in the lower right-hand corner, you'll see a ground plane with a coax having its shield tied to it. The center point feeds the little quarter wave antenna part way up where the characteristic impedance matches. You can also have disks as shown in the upper right. In this case, energy flows from the current at the center out to the outer rim where the capacitance causes, like a capacitive hat, it causes a voltage change. No current can flow around the outside. So that's the high impedance point. The low impedance point is the center. Directly below that, you see implementation of two of those on a PCB. You can do other things. For example, in the lower left, you'll see a little rectangular patch that's fed by a piece of coax. Patches can resonate too. You can buy little component antennas like are shown in the middle, or you can, on the light green board with a bunch of patches on it, you can see that they're all tied together. You can faintly see they're all tied together with propagation lines so that they're all properly spaced and phased so that you have a very highly directional phased array. Okay, but not only do wires resonate, plates resonate too. One of the things people have done have been to take metal plates and vibrate them acoustically and throw white sand on them. The sand, wherever the plate is actually vibrating, will bounce around and move. However, where there are nodes and nulls in that, the sand will accumulate. So you can see the transition points between where the vibrating nodes are. There are many, many different patterns that form at different frequencies, but they tell you how it's going to resonate. There are many multiples, as shown in the upper top, many multiples of wavelengths that will fit. They've been categorized and charted as down below in the lower left. They're used to basically make quality musical instruments, such as in guitars and violins, as shown in the lower right. Obviously, they want all frequencies to come out well so that the notes all sound good and you don't have any clunkers. In the bottom in the middle, you'll see a plate that's being driven in two different modes. In some modes, you'll see that it has multiple standing waves in one direction, left to right. In other cases, it's top to bottom. So plate resonances are real, and physics repeats itself. So let's talk about this. We started off with an LC and showed how it resonated, and talked about a quarter wave antenna and show how it's high impedance on the ends but low impedance in the middle. But over at the right, you can see that there's another plate that is resonating. And you can see that in the red areas that there's a lot of motion on the sides of the plate and almost no motion in the very center for this mode. If you look directly below that, there are plots. In one going between the narrow faces, you'll see there are two humps of energy, okay, based on the frequency of excitation. If you go to the next plot down, you're seeing that it's being excited in the long dimension, and you also get two humps. If you excite it otherwise, you get, shown at the bottom, you get a combination of those. So plates actually do resonate. There's a couple of examples of that in the middle for microstrip antennas. Down in the lower middle, you'll see a metal patch, and you'll see an E field direction across there. And it also tells you where a half wavelength is. There's a feed wire and the ground underneath. That, when covered with plastic, is called a plastic radome antenna, as shown in the lower left. So what is this? Well, what I see is a fat half-wave dipole antenna. It's just a little wider than a piece of wire. The charge can accumulate on the left edge or on the right edge, and it can slosh back and forth between the two with currents flowing. And as it flows, it's going to create a magnetic field. As it starts to flow and the charges equalize, the collapse of the magnetic field will drive it the other direction. So it continues to slosh back and forth. Also, because it's very wide, it's not very lossy. So the amplitudes of these oscillations can be very high. So because of its width and its mode, you can tell that lambda over 2 is equal to its width, and hence you can calculate the frequency from the speed of propagation. But if you look in the other direction, guess what? It also can resonate that way. Well, what if this is a rectangular board instead of a square board? Well, then you'll have a different frequency of that oscillation. And what is this? How is it going to work? Well, guess what? You have a disc resonator. Energy from the outside can slosh to the center, and from the center it can go back out. And so you also, by looking at the speed, you can calculate what frequencies of fundamental will resonate on here. You can also then apply and find the harmonics. But what about this? What is this? I don't know what it is, but let's look at it from just the general geometry. Mostly I see non-parallel edges, which kill resonances because the energy can't bounce back and forth between them. Every time it bounces, it's going to change direction. Every time it goes around a corner, it's going to lose some. It does have two parallel edges, but the length to width ratio is less than about 3, so it's not very long. And it has open ends on the board, which does not have parallel edges. So most of that energy is going to leak out if it gets in there over a very short distance. Thus, this board would not make a very good resonator. In summary, PCBs are filled with conductors of all different types. Depending on the length, termination, and proximity, any one of them could become resonators. There are a whole lot of them. They all have to be checked. So how are you going to do it? You need to do it quickly. If they resonate, what can they do? They can radiate energy, such as you don't pass your emissions or you become susceptible to other EMI, or it can distort the signals. Their sensitive frequencies can be calculated. Radiation and susceptibility problems can be solved early if you know what to look for, and an intuitive vantage point can help spot these quickly and determine whether they need more study. So that's the presentation for today. I want to thank you very much.